Hello, welcome to Einstein's Mechanics. In this episode, we are going to talk about homogeneous and non-homogeneous differential equations. And also, we will look at how to test if an equation is homogeneous. Are we okay? So, with a homogeneous equation, we are going to get an equation in the form a dy on dx is equal to a certain function of x and y. Are we okay? Where it is going to be a function x y divided by x this way. Are we okay? So this is what we are going to refer to as a homogeneous equation. And then again, we are also going to consider first order differential equation. We've already talked about the order of the differential equation, which is the power of the highest derivative. So we are going to deal with first order differential equation. We also have a homogeneous equation defined as an equation or is a differential equation which has 0 as a solution. Are we okay? So our homogeneous equation is going to have 0 as its solution. So for example, if I have this expression, d square y on the x squared plus 0.1 dy on dx plus 4y is equal to 0. This is a homogeneous equation. So we can see that this is what? A second order differential equation. As I said, most of our analysis is going to be based on a first order differential equation. If it is having 0 as a solution, just as in this case, then we can also see a non-homogeneous equation in this way, such that if we say d square y on the x squared plus 0.1, the same equation, but we are writing it to be non-homogeneous. 2 sine 2x plus 5 cos 3x. This is a non-homogeneous equation because it does not have 0 as its solution. Are we okay? So now that we have this idea, let's look at the best way to test for homogeneity. It is very important that we can classify equations to be homogeneous and also not to be homogeneous, not just by the definition, but a test will also help us. So let's look at it. So here we are going to test for homogeneity. If I give you an equation and you are not sure if it is homogeneous, this is a way to go by. So first we said we are going to look at first order equations, differential equations, and it is going to be in the form dy on dx is equal to a certain function of x, y. Are we good? So first, if I give you an equation in this form and you are to test for the homogeneity, this is what we do. First, you are going to let your y in the function be equal to a certain constant. I'll call it lambda y, and also the x in the equation to be also equal to a certain constant lambda x. Are we okay? Okay, so this is what we are going to substitute into the equation. So if we are able to substitute the y and the x into the original equation and we get the original equation back after we've done the substitution, then that equation is going to be what? Homogeneous. So this is what I mean. For example, number 1, if I have a dy on dx to be equal to a certain function y on x. To test if this is homogeneous or not, I will do my substitution. So solution, I'll let my y be equal to lambda y and my x to be lambda what? X. So I'll put it into the equation. And when you look at the equation, I have there's another y. So my y is going to be lambda y on the x, which is the x is lambda x, right? Equal to y should be lambda y and lambda x this way. So after substitution, I can see that this lambda can cancel out to give me dy on dx here. At this place too, I'm going to cancel out to get my y on x. So after doing my substitution, I can see that I'm getting my equation back, meaning the given equation is homogeneous. Are we okay? Very simple. So this is a first way to solve for homogeneity. Now let's look at the second example. I have dy on dx to be equal to x squared plus 3y squared. When we are done, I'll give you a clue to help you solve for objective questions. So if I have plus y squared, so this is my equation, and I'm to test if this equation is homogeneous. So first, what do? I'll just let my y to be lambda y and my x to be lambda x. So doing the substitution, I'm going to get the lambda y on the lambda x equal to lambda x all square plus 3 lambda y all square. Everything on lambda x square minus the x will be lambda x multiplying y lambda y plus y square lambda y square. Are we okay? So let's try to break this one down and see if after we factor the constant out, we are going to get the original equation. So this is what we are going to get. At the dy dx side, we are going to cancel out to get our dy dx should be equal to, when you expand the equation, you can refer back, you are going to get lambda squared from, so let me write the equation again so that we can use it to continue from this side. So we have the lambda y on the lambda x equal to lambda x squared plus 3 lambda y squared. Everything is lambda x squared minus lambda x lambda y plus y squared all squared. So from here we can cancel out from this side to get our dy on dx equal to, when we this part the square is not here, everything is raised to the power square like this. So when we expand this, we are going to get x square lambda square plus, when we expand this, we are also going to get 3 lambda square y square this way. And here we are going to get x square lambda square minus, when we multiply these two, we are getting our lambda square xy plus the same thing lambda square y square. This is just a matter of you doing some substitution and some expression. So x is going to be, we can do some factorization here. On the top side, we can factorize this out, leaving x squared plus 3y squared. So at the denominator too, we can factorize lambda square out, giving us x squared minus xy plus y squared. So we can see that they can cancel out to give us dy on dx to be equal to x squared plus 3y squared on x squared minus xy plus y squared. Are we okay? So we can see that this is back to the original equation, therefore the equation is homogeneous. Are we good? So one thing we should take note is that after the getting your lambda outside, you can see that the power of the lambda is always going to match with the one of the equation. Here, when you multiply the one or you add the powers, you're also going to get 2. Are we okay? So we can see that it is homogeneous. The powers, they match. They are of the same power. We will solve an example where we can see that the equation is not going to be homogeneous. Let's solve the third example. This is just a test. So in a question where you are to test for homogeneity, this is an approach to use. Now the third example. Test if our equation dy on dx equal to 3xy on we have x squared is homogeneous or not. So here we are going to say let our y be equal to lambda y and our x be equal to lambda x. So straight away we put it in lambda y on the lambda x equal to 3y all square plus lambda x lambda y, everything on lambda x all square. So here we are going to get our dy on dx after cancelling out. We expand this to get 3y square plus lambda square xy on lambda square x square this way. So when we do our factorization, we can bring this out, giving us 3y square plus xy, lambda square out, giving us x square. So you can see that they are of the same power as the equation. You add 1, they are all going to be in power of 2. So you cancel out, you are still getting your equation back, meaning the equation is what? Homogeneous. Let's solve another example to test for homogeneity. Now let's find out if the function dy on dx equal to 3x squared plus xy squared is homogeneous. Now solution. We let our y be equal to lambda y and our x be equal to lambda x. So the lambda y on that is going to be equal to 3 lambda x squared plus we have our x lambda x lambda y all square this way. So we are going to cancel out here to get the y on dx should be equal to, let's do the expansion, 3x squared lambda square, right? Plus when we have our lambda x here, let's expand this to be x lambda square y square from this part. Straight away we are going to get 3x squared lambda square plus, now let's do the multiplication. We are going to get lambda cubed x y square. Is that it? Yes. If we try to do some factorization, we are going to get lambda square out, giving us 3x square plus lambda is cube over here. After taking out, it is going to be lambda xy square. So we can see that there is still a lambda in the equation after the factorization, which makes this equation non-homogeneous. So you cannot solve this equation using homogeneous approach. Are we okay? And from the question to the powers, you can see that the first one is square, but this is 1 plus 2, this is 3, so they did not match from the powers. Are we okay? Let's get our last example in this episode to test for the homogeneity. Now let's solve for this. dy on dx is equal to the natural log of x and that of y. So let's see if, let me add some x minus y on x plus y. So this is our equation we are going to solve. So solution, we let our y be equal to lambda y and our x be equal to lambda x. So let's put it in the equation. So this is what is going to have. First of all, this is log functions, and I can manipulate them to get dy on dx. Remember, if this is subtraction, this is the same as length of x on y, right? Yes, plus x minus y on x plus y. This is the same equation written. So from here, I can do my d lambda y on lambda x. So please pay attention how I write the lambda and the x this way, equal to function of, we have, let's put it in on lambda y plus lambda x minus lambda y, everything on lambda x minus lambda, this is plus y, that way. So on the left hand side, we are getting our dy on dx, since they will cancel out, equal to, so at this point lambda can also cancel out, giving us the natural log of x on y, plus here we can factorize our lambda out, giving us x minus y. We can also factorize lambda out, giving us x plus y. So they can also cancel out from here. So at the end of the day, we are getting the original equation back as natural log of x on y plus x minus y on x plus y, meaning this equation is what? Homogeneous. Are we okay? All right. So this is a simple approach to test for homogeneity of an equation. Are we okay? Let's solve the last example. So here I have dy on dx is equal to the fourth power plus 3xy on x squared. So if we are to test for the homogeneity, first, what do we see? Let's consider the powers first. This is raised to the power 4. This is going to be 1 plus 1. This is 2. So you can see that here is also 2. They did not match, right? So definitely we are going to have something non-homogeneous. Are we okay? But if we are not sure, let's use our normal approach. We let our y be equal to lambda y and our x to be equal to lambda x. So we do the substitution, the lambda y on the lambda x. So here we are going to have lambda y to the power 4 plus 3 lambda x lambda y, this way, everything on lambda x all square. From this side we are going to get, let me use the white, we are going to get our dy on dx to be equal to, let's do the expansion, lambda to the fourth power y 4 plus 3 lambda square xy. Everything on x square lambda square. This is going to be equal to dy on dx is equal to, we are doing some factorization from the top side. We can factorize lambda square out, giving us another lambda square y to the power 4 plus 3xy. Then here too we can bring lambda square, giving us x square. So even if this cancels out this, we still have lambda square in the equation, which makes the equation non-homogeneous. Are we okay? So this equation is non-homogeneous. Alright, so this is an approach to test for homogeneity. Are we good? This is an approach to test for homogeneity. We will solve more examples in the upcoming episode. Thank you and see you in the next episode.